This video addresses the question of what is signal processing at a very broad and heuristic level, and it is intended for undergraduate students who are just starting a course on signal processing. So let's begin by asking ourselves, what is signal processing? Now, if we want to address this question, then we need to look at two concepts that lie at the heart of signal processing. The first one of these concepts is signals, and the second one of these concepts is systems. So let's ask ourselves, what is a signal? Now, in the parlance of signal processing, a signal is anything that conveys information. And here the word thing is in double quotes because it literally could be anything. If the color of my shirt that you are watching on the screen conveys any information to you, then that is a signal. Now, I like to make two broad classifications of signals. One classification is that of signals that are either man-made or engineered. The other classification is that of signals that are natural or come from physical phenomena. So let's take some examples of these signals to get a better sense of what we mean by signals. So here is a man-made signal, which is like count on a Facebook post. Now, why is this a signal? Because the Facebook management gets some information out of this knowledge. So this becomes a signal. Another man-made signal is per hour frequency of different search terms in a search engine. For example, Google is looking at when do people search for pizza, for example. That's conveying some information to them that they can use to display ads. Tick-by-tick price of any stock, for example Apple stock, that conveys you information. You might be interested in figuring out whether you want to buy the stock or sell the stock. Ratings of different movies on IMDb. If you are a movie buff, then you go there, look it up. It is conveying information to you. It's man-made, and it tells you whether you should watch a movie or not. Let's come to the examples of natural signals. Voice, speech of a person. For example, you are hearing my voice, and hopefully it is conveying some information to you, so it is a signal. Vibrations generated by seismic activity. It's a signal because it tells you something about perhaps if an earthquake is forthcoming or not. Temperature and pressure across the earth. You'll read about the temperature and then dress accordingly, conveys some information to you. Any visual scene, the video that you are currently watching, this is hopefully again conveying some information to you, becomes a signal. Heartbeat of a living person. Doctors use that to figure out whether a person is healthy or not. Again, becomes a signal. So hopefully this convinces you that there is no one unique way of describing a signal. It literally is anything that conveys information. So then what is signal processing? Well, as the name implies, it's processing of signals. Now, broadly speaking, signal processing is used to do two things on signals. The one is it can be used to extract useful information from signals of interest, and we'll see examples of that. Or it could be used for manipulation of signals of interest to produce desired outcomes, and we'll see examples of that too. So let's say here is your signal processing black box, and the signal that you are dealing with is seismic activity. Now, you can use signal processing to extract information such as, is a tsunami coming? And if so, where is it going to strike? So this is the example of extraction of useful information from signals of interest. Stock price, that's a signal, and the information you want to extract is the stock likely to increase or decrease in value? Again, signal processing will come into the picture for extraction of information. Music. Now this is the case where you're not extracting information, but you are manipulating the signal. Music is a signal for you, and you are interested in, for example, increasing the bass or treble of that signal. So that's manipulation of the signal to produce desired outcome. and that's what you call, for example, an equalizer. Sound, for example, my sound. If you are hearing any background noise, you could use signal processing techniques to cancel some of the background noise, which is called noise canceling. So again, this is a case where you are not extracting information, but you are manipulating the signal to produce desired outcome. Here the desired outcome is that you want to reduce the amount of noise. So the question is, if signal processing is about extraction of information or manipulation of signals, how do we do it? Well, the short answer is there is no one way of doing it. It really depends upon the signal type, the information that you are interested in, and or the intended effect that you want to have on the input signal. Now, signal processing effectively is a large collection of mathematical and computational tools, each one of which is suitable for specific tasks and specific types of signals. And as you become experienced, you get to learn which tool should be applied in which situation. Now, at the undergraduate level, to which this video is being addressed, the reality is that only a very tiny fraction of the world of signal processing can be taught. And that worldview of signal processing is taught mostly based upon the following simplistic view. You have a signal and you are interested in some output, and what you do is you input that signal into a processing block where signal processing happens to get the desired output. Now, in the parlance of engineering, this processing block is termed, as you would hopefully know, a system. So what is technically a system? Well, a system is anything that takes inputs, it could be more than one input, and generates some outputs. Okay? So again, I'll make two broad classifications of systems. There are engineered systems and there are natural systems. Take some examples. Cell phone, that is an engineered system. For example, I would say that a cell phone takes input as voice and generates output as radio waves. A digital camera, that is again a system. The input it takes is a visual scene. For example, the video being recorded, this is the scene, which is the input. The output is the image that you are seeing on the screen. So between this input and output sits a system. MP3 player. The input to an MP3 player are bits, the file that you store on your MP3 player, and the output is a musical sound. These are all examples of engineered systems. What are some examples of natural systems? Well, brain. Human brain takes input as 5 senses and it generates output, which are actions. Lungs. Again, a natural system. The input is oxygen, output is carbon dioxide. By the way, I want to make sure you understand that what I view in a system as input and output could be different for my problem, and it could be different for your problem. In a mountainous region, if you talk about acoustics, for example, I shout something and I hear the echo back. Well, the mountainous region is acting as a system. The input to that system is sound, and the output is also sound. The echoes are the outputs. Now, signal processing is mostly focused on building engineered systems to do signal manipulation. Signal processing does play a role in analysis of natural systems, but most undergraduate classes, of course, do not focus on that. But signal processing systems are always engineered systems. Okay, let's address one more question in this video, which is it signal processing or is it digital signal processing? Is there any difference between the two? Well, the terminology of digital signal processing, and that's a very biased view of mine, is a relic from the past when analog signal processing was much more or at least as much as prevalent as digital signal processing. I haven't given you the definition yet, so let's talk about what exactly do we mean by digital signal processing. Well, DSP, or digital signal processing, is basically processing of signals or implementation of systems where the implementation is carried out inside a digital system, digital hardware, which could range from microprocessors, microcontrollers, special purpose chips that exist in our cell phones, PCs, tablets, and so forth. And digital signal processing, when we talk about it, it basically requires three things. One is, of course, you need basic understanding of signal processing concepts. The second is you need a digital hardware. That's where the digital in DSP comes from. And the third is the implementation is going to happen on this digital hardware. And so what we need is some software implementation on that digital hardware. Now, one thing is important to point out here. DSP does not mean that the system cannot have any analog components. The analog components will exist to interface with the outside world, for example. The main distinction is that the processing happens in the digital system and not in the analog components. So what is analog signal processing then? You might have guessed by now that it is where the processing of signals is carried out using analog components like resistors, transistors, capacitors. So a question to ask is, why is digital signal processing winning? Which in my view, it is. And there are numerous reasons for that. I'll give you some of my own biased views. The first one is that DSP allows repurposing of the same hardware for different applications. You have the same cell phone. You can use it for different DSP applications. Whereas for an analog signal processing, a specialized hardware needs to be built for different problems. All you need to do for repurposing is write a different software. So if you have cell phone, you can think of as apps. You have one app for doing one thing, one app for manipulating images, another app for manipulating videos. Same hardware, wrote a different software, you are getting a new system. Here is another key important thing. Any errors in system implementation, they are very easy to fix. All you have to do is that you rewrite your software and you do a software update. For example, if something doesn't work in your app, the app developer will update the software and now you will have better way of dealing with it. Digital systems perform in exactly the same fashion till something breaks. Now, it's not that they don't break, they do break, but till something breaks, their performance stays the same. On the other hand, performance of analog systems varies continuously with factors such as temperature. What they do today, tomorrow there will be a little bit of different, even if you cannot tell the difference. Now, cheap storage of signals also is possible using digital signal processing for a long period of time. That is not always possible using analog signal processing. It could take you, the cost could be high. And perhaps one of the most important factors is that digital processing power is cheap and it keeps on getting cheaper because of the Moore's law. And here is a pictorial representation of that. As you can see on this figure, in the 1960s and 70s, $1,000 will only buy you 100 calculations per second. And today, or in 2000, the $1,000 now buy you 100 million calculations per second. It's a logarithmic plot. It's exponentially, the power of computation is exponentially increasing. Now, so a natural question to ask at this point is, are there any disadvantages of digital signal processing? And the answer is yes, there are some disadvantages. The first one is that if the original signal is analog, for example, think of it as voice, then it first needs to be brought to the digital domain, and there is always some loss associated with it. In fact, there is a huge field of signal processing called sampling theory that deals with this loss and tries to minimize this loss. DSP systems also suffer from finite precision arithmetics. So for example, if you have an 8-bit system, it can only have 2 to the 8 equals 256 different values to represent a signal. Analog components, of course, can take on as many values till you reach saturation. That brings up the issue of what's called quantization in signal processing. Again, a big thing that you have to address if you are dealing with digital signal processing. DSP systems tend to consume more power than analog signal processing systems. They have more power requirements. Now, despite all these arguments, the reality is that the advantages of digital signal processing far outweigh its disadvantages. You will get people who will argue, for example, that disadvantages are way more in certain applications, but these disadvantages are getting lower day by day. And the reason for that is because, first of all, signal processing theory is advancing very rapidly to get rid of the issues associated with sampling theory, with quantization. Digital hardware is getting better, which is making it possible for us to use digital systems at very low power. And we already know that we are getting these cell phones and all these other devices with hours and hours of battery life. So hopefully that provides you a basic understanding of what signal processing is. I'd like to conclude this video with a big picture view of signal processing to remind you of the things that we have talked about. So in signal processing, what you start with is there is a physical or a man-made phenomenon. For example, a person singing a song, that's a physical thing, the voice coming out of the person's mouth, or social media interactions. And here you are dealing with either continuous or discrete signals. So that's your starting point. And then what you do is figure out a way, how do you want to acquire or measure this phenomenon? And that's what is called sampling theory, a big part of signal processing. It often involves a hardware device, for example, an analog to digital converter at the very least, if you are dealing with things like voice, along with possibly some software. And the purpose of this interface sampling theory is to basically provide you a good representation of the signal in the digital domain. So the thing that comes out of that is what's called a discrete signal. Now, once you have this discrete signal available to you, then you can ask this different questions. For example, one question you could ask is, how do you analyze the phenomenon? So you use that signal and you process it to analyze the phenomenon. Now, most undergraduate classes for processing focus on discrete Fourier transform or short-time Fourier transform and things like that. When you go to graduate school or higher classes, you can learn more sophisticated techniques for doing analysis of the phenomenon, extraction of information. Now, the star here means that you don't have to have this component in your signal processing system. The output of this analysis part, if there is an output, would again be a discrete signal. You could also ask, how do you manipulate the phenomenon? For example, you could analyze the phenomenon. You could say, you look at my voice, figure out whether there is any tone above, let's say, 10 kilohertz, and then you want to get rid of all the information above 10 kilohertz because it's going to consume perhaps bandwidth and so forth. So the question you can ask at this point is, how do you manipulate the phenomenon that you are given in terms of a discrete signal? Now, again, there are many ways of doing that, but at the undergraduate level, the focus is on what's called digital filtering, basic filtering techniques that you learn. At the graduate school level, you learn further adaptive filtering techniques and more advanced things. The output of this step would again be a discrete signal. And then depending upon what you are interested in, you may or may not have, again, this next component is you may be interested in reconstruction of the phenomenon. For example, when I'm recording my voice here, recording this video, the intention here is that it would be replayed back. So my voice is being digitized, but at the end of the day, you want to reconstruct my voice from that digital signal so that you can hear it. That's called reconstruction. And that reconstruction is again part of sampling theory. It again involves often a hardware device with some possible software. So this is a big picture view of signal processing for students at the undergraduate level. Just a recap, you start with a physical phenomenon. That's your signal. You may have sampling going on and reconstruction. Most undergraduate classes do teach you that sampling theory, reconstruction theory. Then you have a little bit of processing that happens inside it, which is either for analysis of the signals or it is for manipulation of the signals.